No. Because oh wait. Let me go down.
Yeah, that's what I'm trying to say. I'm actually just like, I kind of just like don't, it's like, I don't care about accuracy, I'm just like thinking like, what's the big picture? That's exactly what I was saying. That's not the graph, I just keep drawing the same fake curve every single time, just to remind myself about what the definition is. You don't have to, if you want to put more effort in and make your graph accurate, that's probably a good idea too, I don't know. I just never do that. Because the algebra is just going to work itself out, right? The picture isn't important. The picture is just there to help you just think about what's actually going on. So that's kind of. Someone's stealing my just whistle while do math move. No particular tune or purpose. So these limits are not even that hard, right? Do a little bit of algebra and everything's cool.
Yeah.
Yeah. You guys getting negative 1/16?
Yep.
Average you both ways? Okay, I'm too slow. Bam! Negative 1/16 is the answer, and thus the equation of the line y minus a fourth equals negative 1/16 x minus 4.
Yay.
Pretty awesome. And again, it makes total sense, right? Because if you draw the picture now I will care to actually draw an accurate graph. 1 over x looks like this. And does it kind of make sense that if I get out here to 4, that the slope of that line is going to be a tiny negative number?
Yeah.
Makes total sense. Yep. M equals negative 1/16. Okay. This is pretty cool. By the way, let's see, what should I do first? Yeah, there's a name for this. This thing that we've been doing for the last 10 minutes, the tangent line problem, yeah, or these things that we've been computing, these are called derivatives. So this is a derivative. Yeah, big moment in your life. If that was a word that you've heard people throwing around, now you know what it is. A derivative is, at least the way I'm doing it, hold on, put your hand down, Emma. Whoa, yeah, you can do that. This is a stupid thing to write on the board. This is a derivative. What is a derivative? A derivative of, so I'll write it. The derivative of f at x equals a, which by the way we have some notation for. And the notation is we write f prime of a. The derivative of f at x equals a is, by definition, well, it's the slope of the tangent lines of the curve. So it is either the limit as x approaches a of f of x minus f of a over x minus a, or, and these can be proven to be equivalent, the limit as h approaches 0 of f of a plus h minus f of a all over h. So that's a derivative. We've been computing derivatives already for the last 15 minutes. Let's actually do one now using this new language. So this is maybe the easiest one yet, but it's kind of cool. So I give you a function, f of x equals x cubed, and now I'm sort of abstracting away from the geometry problem to some extent. And now I can just ask questions like, hey, what's f prime of 2? And we pronounce that f prime of 2. But what it really means is the derivative of f at x equals 2. So do it. Do it just like one of the two ways.
So like no graph.
You can make the graph. You can still make the graph to help you think about what's going on. But I'm no longer asking a geometry problem per se. I'm asking just kind of a calculus problem, I guess.
Do it one way.
Yeah, just do it one way, and then put a box around your answer, and then make sure everyone at your table gets the same answer.
It's crummy sauce.
Yep.
No, just like factory.
Oh, you did factory and
No,
can't
no, no, just do like division. Plug in two, just plug in two and make one of them. I'm just doing this. You can just, and then give you the quadratic, you don't have to like.
Yes.
Yeah.
Yep. We just do that in class, right? We just talked about that later, me and you.
Yeah, with the.
All I know is crummy sauce, right?
Crummy chops. Yeah. So you guys almost done?
It's
Oh.
crummy, like the first thing, not cute.
Yeah, I think you added something wrong. No, it's plus. Yeah. No.
So yeah, so it'll be like, okay, so the first
Oh, wait, why
crummy,
did
like
I-
the thing without the cube. So like this would just be F,
Yes.
and then like the cube and 8 is 2. Okay. And then sauce is square the first one, square the first one, and opposite side, then the product of the two crummies. And then
No,
square
the answer is
second
definitely
one.
12.
But I don't have to think about it.
Wasn't planning on going over this. Is the limit as x approaches 2
That's all.
of f of x minus f of 2 over x minus 2. So is the limit as x approaches 2, x cubed minus 8 over x minus 2, and then you just factor this, right? I feel like we even did this exact problem.
Probably.
X minus 2,
Yeah.
x squared
It's really
plus 2x plus 4. Wow. Cha. Answer 4 plus 4 plus 4 equals 12. You guys with me?
Yeah.
Alright, so. Cool. Alright, Calvin, before we move on. Alright, at least for like 1 minute, I'd like to have a little conversation kind of about what this all means. So, you know, we sort of reviewed, I guess we'll do this, we'll just continue to keep doing this again and again, that the entire point of the tangent line problem is that it solves a physics problem for us. And the physics problem that it solved is that I had some position versus time curve, and I wanted to know at some particular time A what the instantaneous speed was. And the way I basically did this was to, well, just exactly like what we did, right? We picked a time, and now I'll sort of use maybe t as my variable. So I picked like a time t, and here I am at a comma f of a, and here I am at t comma f of t. My goal is to find the instantaneous speed at time a. And what we said is, well, finding the instantaneous speed is hard, but we can what we can do is we can find the average velocity on the interval at. And the average velocity on the interval at is the change in position over the change in time. And what we said, therefore, is that the instantaneous velocity at A, or maybe I'll say at t equals A, is then just kind of the limit, right? It's the limit as this change in time. It's the limit as the change in time approaches 0 of the change in position over the change in time. Okay. And what we have found is that we had to draw this tangent line in, and that essentially what we're doing, when we draw the tangent line, what we're doing is we're converting our physics problem of finding the instantaneous speed, we're converting that into a geometry problem. It's actually some sort of deep philosophy of math going on here, which we talk about in logic math. But in my opinion of what's going on, or tell me if you agree, I'm taking a physics problem of instantaneous velocity, then I'm converting it into a geometry problem of finding the slope of a tangent line to the curve. And then I'm taking the geometry problem and I'm solving it with sort of algebra plus infinity. I feel like that's what's really going on. All right, so by that understanding, the tangent line is just kind of this mathematical object which I introduce into my problem in order to be able to solve it. But I actually think it's more than that, and I would like to reference something that you have some experience with, which is in freshman physics. You talked about, hopefully those lectures did not go that well the other day. I thought you guys knew things, maybe you forgot, or never learned them. So when you spin stuff, can someone give me like a 10-second explanation of what's going on right now? Spinning, yeah, more but more physics words. Yeah,
Gravity.
Accelerated towards the center.
Yeah, so this is called centripetal motion, and in fact, you learned, hopefully in physics, although I won't go into the whole explanation all over again, that what's really happening to produce this motion is that I'm pulling on the object, I'm pulling on into the center, right? As I continue to be able to spin this object, what I'm actually doing, besides hypnotizing you, is I'm hypnotizing myself. I'm pulling slightly on the object at all times, dragging it into the center, okay? And I'm exerting a force, and that force is causing the object to accelerate. Okay, and then what about the velocity of the object? Treated as a vector. What do we say about that? Yeah, this is like a thing that you learned, that you may have understood or you may not have, that the velocity is, so the force is acting inwards towards the center, and the velocity vector is tangent to the circle, okay? Yeah, and what that really means, or at least my understanding of what that means, is that when I spin this thing, then what I'm really doing, so what that means, what that means to say that the velocity is at a given second, this is really the kind of question we're asking, is a calculus type question, right? What is the velocity at any given second? Well, the velocity in any given second is sort of telling you what the thing's going to happen what's going to happen if you let go. So here I am, I'm spinning this thing, right? And at every single second, to keep this from moving, let's suppose no gravity, because it's just more fun for many different reasons. But gravity is kind of irrelevant to this discussion. So if there's no gravity, and I am causing this thing to move by pulling in on the center, if I should suddenly let go, what's going to happen? Should I just do it?
Straight line.
Oh, that was terrible.
Now
Let's
it's
try
a
that
straight
again.
line.
Yeah, I know, because I kind of wussed out the last second because I would have hit him in the face. But now I don't care about that. So, boom, boom, boom. Whoa. Okay, so it's going to go flying over there, right? And so what actually happens is the second that this is like physics teacher envy going on here. This is what's happening, right? At the second that I let go, I am ceasing to cause a force on the object, right? And thus, wait, I'm saying something deep. So Matteo, the second I let go, I am no longer exerting a force on the object. And since I'm no longer exerting a force on the object, then I'm no longer accelerating the object. And if I'm no longer accelerating the object, then I'm no longer changing its velocity. That's what acceleration is. And if I'm no longer changing its velocity, then what will its velocity do? It will stay the same. In fact, that's what velocities do. That's Newton's first law, which is that things are just going to keep on moving forever unless you mess with them, right? And so what happens is at the second that I let go, I retract the force, the acceleration is now gone, and the object just moves on, and if there were no gravity, it would just move on in this path forever. Okay, the point of this long-winded ramble is that the tangent line is not just a mathematical tool which I insert into a problem in order to be able to solve it. The tangent line actually has a physical interpretation. What is the tangent line to a curve at a particular point A?
If you let go at that point.
Yeah.
If it stops going on the curve.
If the acceleration stops. Acceleration stops.
Yeah, all you guys are saying basically all the same thing, and it's basically exactly correct, right? The tangent line represents, but I'll just say it slightly differently. What the tangent line represents is the path that it represents the path that the object would take, or rather, it represents the position function for the object if it continued going at that point A at the speed that it was going at point A. In other words, if you take the object's velocity at time A and lock it in, and lock in that velocity, then that tangent line represents the position versus time curve of what that object would do. Does that make sense? I think it does. Okay, cool. So what do we have time for? Yikes! I guess we have time for one thing. We have now seen a bunch of derivatives. I think that some teachers are kind of bad at this, and our textbook is quite bad at this, at distinguishing between these different things. As far as I'm concerned, a derivative is like what we did over there, right? And can someone, like what, so maybe even just tell me now, like what is a derivative? There's many different answers to this question. I'm probably going to keep asking this question over and over again. Yeah, Busis, give me an answer. What's a derivative? It's that formula thing. Okay, but a more specific mathematical answer. What kind of mathematical object is it? Is it, for example, a triangle? Is it a line? Is it a number? Is it a set?
Number.
Is it a, yeah, the answer is number, okay? A derivative is a number. That's a key concept, right? A derivative, because a derivative is a limit. And the limit, assuming it exists, is a number. Okay. Good. However, oftentimes, what people mean when they say the derivative is not really the derivative, but the so-called derivative function. So what is a derivative function? If we were being careful, we would always call it derivative function, but that's kind of lame. So later on, we just start calling it derivative. But the derivative function is a function which outputs derivatives. So now I'm going to do basically the same thing that we did before, but now instead of figuring out the slope of the tangent line at A, I'm going to figure out what the slope of the tangent line is at X, a point in general. So if I take an arbitrary point X on some curve F, then how should I choose the point which is a little bit more than X? What should I call that? X plus H. Excellent idea. And so this point is now x comma f of x plus h, and thus, can somebody give me a definition for the derivative? So, yeah. Can someone give me a definition for f prime of x? Right, Fleischman?
F of x plus h minus f of x over h as h goes to 0.
Yep.
Start with the h goes to 0. But
Yep, it is the limit as h goes to 0. It's exactly what we've been doing, but now in general. Okay, so now, and we have to finish this before the bell rings, I can give you a function, f of x equals root x minus 4, and I can just say, yo, what is the derivative? And when I say that, what I'm really doing is I'm saying, come up with a formula which for any x whatsoever will output derivatives.
We've been fortunate enough
Okay,
to
go.
be given complimentary tickets to the movie The Duff that's showing at the AFI February 11th. The pass admits 2 students or 2 people to the showing. If you're interested in picking up the passes, they're here at the attendance office. Again, it's February 11th at 7 o'clock. I'm sorry, at the Regal Majestic, not the AFI, at the Regal Majestic, and we do have passes. Also, congratulations to our wrestling team that defeated Einstein on Saturday. Congratulations to our girls JV basketball team that defeated Churchill in their last season game. And also congratulations to our boys varsity that defeated Churchill. Thanks and have a good afternoon.
You guys all with me? All right, so do that limit out. Tell me what you get.
Wow.
No, you have to do it, Calvin. I don't know why you put your books away 5 minutes before the bell rings. Who do you think I am? I go 2 minutes after the bell rings. 2 minutes before.
You really
The
should.
wrong guy. So are you guys multiplying by the conjugate? It's like the thing to do, right?
Yeah.
Yeah. Liar. If you did it right, it all works out kind of nicely. Yay. Is this what you guys got?
Yeah.
You get 1 over, as h goes to 0, you get root x minus 4 plus root x minus 4. Okay, that was a little bit rushed. Eric, we good? You got that? Yeah, so the final answer is 1 over 2 root x minus 4. And when people say the derivative of this function is 1 over 2 root x minus 4, what they mean is now this is a formula. This is a formula which, anytime I plug in an x, will give me back the derivative. Did I mess up, Eustace? I feel like I did. Okay, check your algebra later. I'll see you guys on Wednesday.
X minus 4 minus x minus 4.
Because 0. H goes to 0.
Are we okay? Cindy, you got this? Oh, we said, did you turn it off yet?
Not yet.
Okay, goodbye. That was the end of lecture 7. We learned about derivatives. More next class.